Now we will define a few integer functions that will be important for this class. The reason we are defining these integer functions is that whole numbers, integers, form the backbone of discrete mathematics, and we often need to convert fractions or arbitrary real numbers into integers. And these are some of the functions to do that. The first of these is the floor function, ceiling function, and the mod function. The floor function takes a real number as a parameter and returns the largest integer less than or equal to that real number. So it takes x as a parameter and returns the largest number that is less than or equal to x. We denote this function with something that looks like this. So for example, if I look at floor of 18, I'm supposed to find the integer that is less than or equal to 18 and the largest such integer, so that will be 18 itself. If I look at 3.75, the largest integer less than 3.75 is 3. With negative numbers it is a little different. Largest integer that is less than negative 4.5 is negative 5. So floor of negative 4.5 is going to be negative 5. Ceiling function takes a real number and gives an integer such that it is the smallest integer greater than or equal to x. We denote this by this symbol where we have these two symbols that we have and we put the number x in between. Once again, ceiling of 18 is 18. If I take ceiling of 3.75, it's going to give me 4. Ceiling of minus 4.5 is going to give me minus 4. Here are some properties of floor and ceiling. I want you to verify this by yourself. Make sure that you're okay with it. If there is something that is not clear, feel free to ask me or discuss in class, etc. Here I have a bunch of statements with floor and ceiling. Your job is to identify whether these statements are true or these statements are false. Once again, you can pause here, and when you're ready you can go to the next slide to review the answers. Now the exact counterexample you may have found may be different, but if your answer in terms of true or false does not match with what is over here, then you should check your answers, see why they're wrong. Alternatively, you can discuss this in class as well. The next function I want to define is the modulo function. Before we get into modulo, first let's look at division and let's look at a relation for dividing the number 101 by 11. Now I can write this as 101 is 11 times 8 plus 13. 101 is 11 times 11 minus 20. I can write this as 101 is 11 times 9 plus 2, and so on. The addition that the division that we generally like is this one. This says 101 is 11 times 9 plus 2. So the way we like to think of this in elementary school is If I have 101 things and I have to share it with 11 people, what happens? And in this case, I would be able to give each one of them 9 and 2 will be left over. The property that we like about this and the one that we don't like about this is this remainder. Here what we have is the number of things that are left is 2. It's too small to divide it any further without breaking them up. 13 is no good because there are too many things left and we don't like these negative numbers. So the definition of modulo operator is intuitively based on this observation that the remainder that we want in this case must be between 0 to 10. And that's exactly how we are going to define the modulo operator on the next slide. So let n be an integer. It can be positive or negative. Let m be another integer. We require that m be positive. Then we can find unique numbers q and r such that n is equal to m times q plus r and r is less than r is greater than or equal to 0 and less than m. In this case, we call n the dividend, m the divisor, q is the quotient, r is the remainder, and this remainder is basically what is going to be of interest to us for a lot of applications. So one example of this we saw in the previous slide is 101 is 11 times 9 plus 2. If I write this as 101 is 11 times 8 plus 13, that's not okay because this 13 is not satisfying this property. Another example, minus 11 is 3 times minus 4 plus 1. In this case, the quotient is minus 4. The remainder is 1. Note that if I write the statement as 11 is equal to 3 times minus 3 minus 2, this statement is mathematically correct, but that's not okay for us to find the remainder because this remainder cannot be negative. It has to be greater than or equal to 0, less than m. So always remember, remainder cannot be a negative number. Now using this notion of division that we saw on the previous slide, we can define the notion of modulo operation. So here we have two integers. N is any integer. M has to be a positive integer. Then if I take n divided by m as a real number, take the floor of that will be the quotient. And if I take the quotient times m out of n, then I will get the remainder. So that's what the modulo function is all about. So to compute n modulo m, we are going to use this formula. So you're first going to compute n divided by m, take floor of that, multiply it by m, and then whatever is left, that is going to be your remainder. And that is the answer to the modulo problem. Formally, we can define modulo as a function that maps z cross z. That means it takes two parameters. The first one is any integer, the second one is a positive integer. It maps to n, the set of natural numbers, such that n mod m is given by this function, which is you first divide n by m, take the floor, multiply by m, and then subtract it from n. So if I wanted to get 5 mod 3, I can do that, and the answer will be 2. I would ask you check the math in here to make sure that you're good with it. We can also compute modulo when n is negative. So in this case minus 5 mod 3. I can first do minus 5 divided by 3, that gives me minus 1.6. If I take floor of that, that will give me minus 2. So if I subtract 3 times minus 2, the answer that I will get would be 1. So we can also write 5 is equivalent to 2 modulo 3, 9 is 0 modulo 3, minus 5 is 1 modulo 3, and so on. Once again, we have reached the check before you go ahead slide. We defined three important functions right now: the modulo, floor, and ceiling. The modulo operation is actually going to be quite important in this class, so make sure you have understood it well. The key requirement for modulo operator is that the answer has to be between 0 and the number with which you are taking the modulo operation, like in this case 7. So I want you to be able to answer the modulo, especially in the context of where you're taking modulo of a negative number, like in this case you're taking modulo of minus 10 mod 7, and also here we have floor and ceiling of negative numbers. That is something some people do find challenging. Answers are at the bottom of the slide, so if they don't match with what you expect, please check with us. We have reached the end of the module, and I would like you to do the review quiz for this module.